So in our last video, we learned how to solve certain equations using radicals. Now in that video, all of our radicals were magically whole number answers, or integer answers anyway. And it was great because we just kind of got our answer and we went on with things. It was good. But as you can imagine, not all roots give you nice clean answers, just like square roots. So we need a process to simplify and break down those kind of radicals, just like we did with square roots. Now, the good news is, if you understand how to do it with radicals, with square roots rather, which you all do, this process is going to be the same thing because we're going to do it still with factor trees. So if you're asked to simplify a radical like this first one over here, the first thing I'm going to do is bust out my factor tree, just like we always do. And when you break down your number, move this a little bit more, what we're going to do here, when we were doing regular plain old square roots, we were looking for pairs of the same number. Pairs because it was a square root. So we would say, oh, there's a pair of 5s, a pair of 2s, those go on the outside. Well, in this problem though, we're doing a cube root. So that means we don't want pairs, but we want groups of 3. So if you look, I have 1, 2, 3 5s. That means I get to put a 5 on the outside. I'll switch colors for that part. So I get a 5 on the outside because I had a group of 5s. Only one 5 for each group of 3. Then I have a 2 and a 2 left over. There's not enough 2s. You need 3 of them to make a group in this problem. So those 2s have to stay inside. 2 times 2 is going to get me 4. So what I'm looking at is 5 times the cube root of 4 for my simplified radical. It's the same process. You're just making groups of 3 instead of 2. My next problem here, I'm asked to simplify, so I'm going to break down my radical. And nothing too crazy here. This part is the exact same process. When I break this down, however, we look at what we have. We're doing a 4th root in this problem, so we need to look for groups of 4 of the same number. And as it turns out, I have 4 2s right here, so I get to put a 2 on the outside. And then I still have a 2 and a 5 left over. They didn't have enough numbers to pair up with. So 2 times 5 is going to make a 10. 10 stays inside. Your answer is 2 times the 4th root of 10. On the last one here, you see that there's a negative 32, the root of negative 32 anyway. So for this one, it's an odd index, so it's okay that it's negative. That's not going to be an imaginary answer. When you see a negative, what I usually do is kind of like with the imaginary simplification. Let's pretend this was positive for a second and just do it on regular 32. So we're just going to do it on regular 32 and we'll deal with the negative at the end. If you break down 32, it's going to break down into a bunch of 2s, 5 2s in all. So we have 5 2s right here. That's exactly how many we need to make a group because we're doing a 5th root. So my answer is just going to be 2. This is actually a clean problem with no more radical. And since it was negative 32, I'm just going to make this a negative 2. And that will be my solution. So when you have your negative on the inside, if it's an odd index, it's not going to be imaginary. Just do the problem like normal and put a negative on the outside. So to wrap up this video, I'm going to introduce 2 problems with variables in them. When you guys first look at these, this is going to look a lot more complicated. But the thing is, it's really not any worse. I'm going to show you the hardest part's already out of the way, which is what we did on the last whiteboard here. So looking at a cube root here, the first thing I'm going to do is break down my 98. So I'm just going to go through and do my factor tree, kind of like I normally would here. This one is actually not going to break down at all. I'm trying to think if that was supposed to be intentional. I thought this one was supposed to break down. Anyway, the way things worked out, you know what? The cube root of 98, that's not going to do anything for us. There's no groups of 3. So the 98 just has to stay on the inside. So I'm going to leave this 98 right there. There weren't enough to make a group. That happens. You just go with it. Now, though, I need to look at my variables. So I have x to the 7th on the inside here. You can think about that like 7 x's all lined up. So 5, 6, 7 of them. You're looking for groups of 3 because we have a cube roots. So I can make 1 group of 3. I can make 2 groups of 3. And there's 1 x left over. Well, I have 2 groups of x's. X times x is going to be x squared. And that extra x has to stay inside there. Now I do the same thing with the y's. Y to the 5th really means I have 5 y's here. Looking for groups of 3, I can only make 1 group of 3. So I toss a y on the outside. 2 y's left over. It's going to be y squared. This will be my answer for that problem. So you do the same thing. You just kind of think about how many variables you can take out. We're going to do one more example, and I'm actually going to change this number because I don't think this one works out. I want to have a number on the outside just for the sake of our example here. So let me actually change that to a, let's go with 81. Let's go 162 actually. Sorry to change the problem mid-video, but I want to make it more interesting. 162, go ahead and practice, maybe even pause for yourself and do a factor tree on it. If you break down 162 though, it is going to end up simplifying. We're looking for a group of 4, and it turns out we have that. So we got our 3's right there. We're going to put a 3 on the outside, and we're going to put the leftover 2 on the inside still, and we have our 4th root right there. Now we just have to look at the variables. If I have 12 x's making groups of 4, I can put 3 x's on the outside, x to the 3rd. There are no x's left over. I only have 3 y's. That's not enough to even make one group, so the y's have to stay inside. And I only have 1 z. That's not even close to enough, so that z has to stay inside as well. So let's run out of space right there, but that would be my final answer for this second problem.